Today's lesson, interhalogen compounds. In this lesson, we are going to learn halogens and then examples of interhalogen compounds. So let's get started. First of all, let's try to learn about halogens. Let's see elements that belong to column 17 in the periodic table. Fluorine, chlorine, bromine, iodine, astatine, and finally tennessine, elements that belong to column 17 in the periodic table. Here we know that from top to bottom atomic size increases. So simply we can show in this way: atomic size of fluorine, chlorine, bromine, iodine, and so on. Here electronegativity of fluorine is 4.0. For chlorine this is 3.0, bromine 2.8, iodine 2.5, astatine 2.1. In this column, astatine and tennessine are radioactive elements. Actually, the elements that belong to column 17 in the periodic table are called halogens. Here, the term halogen, derived from Greek word halo, means salt, and gen means former. So halogen means salt former or salt producer. These elements are called halogens, salt producers, because these elements, suppose chlorine reacting with alkali metals or alkaline earth metals, these elements that belong to column 17 reacting with alkali metals or alkaline earth metals form salt. Sodium chloride, here magnesium chloride, as the elements that belong to column 17 reacting with alkali metals or alkaline earth metals form salts. That is why these elements are called salt producers. In Greek word halogens. So these elements that belong to column 17 in the periodic table are called halogens, salt producers. Physical state of halogens are like this: fluorine is gaseous, chlorine gaseous, bromine is liquid at room temperature and atmospheric pressure, iodine is solid, and astatine and tennessine are solid substances. Let's move on to the next point. Now the point is examples of interhalogen compounds. Let's see some examples. Here, first of all, this one, iodine monofluoride. Again, iodine trifluoride, iodine pentafluoride, iodine heptafluoride. Some more examples: chlorine monofluoride, bromine trifluoride, etc. Another example we can write: iodine chloro tetrafluoride. These are the examples of interhalogen compounds. Now let's see definition of interhalogen compounds. The compound which is formed from two different halogen atoms or from two or more different halogens, then the compound is called interhalogen compound. Simply we can say that the compounds that are composed of two or more different halogens are called interhalogen compounds. Here, general formula of interhalogen compounds is like this. Here n is equal to 1, 3, 5 and 7. Here X is less electronegative atom or element. Here we know electronegativities of halogens, and Y is more electronegative element or atom. For example, iodine trifluoride. Iodine, which is less electronegative atom, that is 2.5, and fluorine, which is more electronegative atom, that is 4.0. So this is the general formula of interhalogen compounds. Another question arises that here values of n is equal to 1, 3, 5 and 7, odd numbers, no even numbers. Now let's see why odd numbers. Let's see electronic configuration of fluorine first. 1s2, 2s2, 2p5, total 9 electrons. Let's see electronic configuration in box method, outermost shell. 1, 2, 3. 2s orbital contains 2 electrons and 2p orbitals contain 5 electrons. 1, 2, 3, 4, 5. Electrons are distributed according to Hund's rule. Here we can consider that fluorine in the interhalogen compounds is sp3 hybridized. 2s, 2px, 2py and 2pz. So total 4 orbitals take part in hybridization to form 4 sp3 hybrid orbitals. Let's see orbital structure of fluorine. Total 4 hybrid orbitals, 1, 2, 3, 4. Here 3 orbitals contain 1 electron pair each and 1 orbital contains unpaired electron. Simply we can show that fluorine 3 pairs of electrons and this is unpaired electron in the sp3 hybrid orbital. Fluorine forms bond with this sp3 hybrid orbital. Now let's see electronic configuration of iodine. Atomic number 53. Configuration is krypton, then 4d10, 5s2 and 5p5. Krypton 36, 46, 48 and 53. This is in short electronic configuration of iodine. Let's write electronic configuration of iodine in box method. Electronic configuration of iodine in box method. 53. This is 5s orbital, 5p orbitals, and iodine has d sublevel, but d orbitals are vacant. So d orbitals 1, 2, 3, 4, 5. These orbitals are vacant. 5s orbital contains 2 electrons. 5p orbitals contain 5 electrons. 1, 2, 3, 4, 5. So we see that iodine contains one unpaired electron. If we consider iodine undergoes sp3 hybridization, then 4 orbitals are formed. 1, 2, 3, 4. Here 4 orbitals take part in hybridization. From these 4 orbitals, 3 orbitals contain electron pair each and 1 orbital contains unpaired electron. With this orbital containing unpaired electron, fluorine forms bond with its sp3 hybrid orbital containing one unpaired electron. In this way, iodine fluoride is formed. That is, formula is like this: 1. Value of N is 1. When it will be 3? Let's see. Now let's see first excited state of iodine. First excited state of iodine. At this stage, one electron from 5p orbital shifts to the vacant d orbital. Now electronic configuration is like this: d 5 orbitals, 1, 2, 3, 4, 5. S orbital contains 2 electrons, px 2 electrons, py now 1 electron because 1 electron shifted to vacant d orbital. Here 1 electron, now d orbital contains 1 electron. Now in iodine sp3d hybridization occurs. That is, in this case, total 5 orbitals take part in hybridization and 5 orbitals are formed. That means here simply we can say that in the outermost shell of iodine, now 3 unpaired electrons. So with these 3 unpaired electrons, iodine forms 3 bonds with 3 fluorine atoms, iodine trifluoride. That is, now it is XY3. Previously it was XY1. Now let's see why it will be XY5. When iodine is at the second excited state, then one electron from 5p orbital shifts to the vacant d orbital again at the second excited state. Then we see electronic configuration like this: s orbital contains 2 electrons. Now 5px orbital contains 1 electron because 1 electron shifted to vacant d orbital. Here 1, here 1, and d orbitals 1, 2, 3, 4, 5. This d orbital contains 1 electron, this d orbital contains another electron. Now in the outermost shell of iodine, total 5 unpaired electrons. With these 5 unpaired electrons, iodine forms 5 bonds with 5 fluorine atoms. With these 5 unpaired electrons, iodine forms 5 bonds. That means iodine pentafluoride is formed. So in this way, here 5 will come: 1, 3, 5. When iodine comes third excited state, then 1 electron from 5s orbital shifts to the vacant d orbital. Now we get this orbital now contains one electron. Here 5p 1 2 3 that contain one electron each, and 5d orbitals 1 2 3 4 5. Here first three 5d orbitals contain one electron each. Now in the outermost shell of iodine, total 7 unpaired electrons 1 2 3 4 5 6 7. With these 7 unpaired electrons, iodine forms 7 bonds with 7 fluorine atoms. That is, odd number is related to unpaired electrons in the outermost shell of less electronegative atom. In this case, this is iodine. So this is the reason for being odd numbers 1, 3, 5 and 7. This is the way interhalogen compounds are formed. Let's move on to the next point. Now the point is reactivity of interhalogen compounds compared to individual halogens. Let's look at the matter. Suppose interhalogen compound is iodine monobromide. Simple example. This is reactive compound, or this one is reactive, or this one is reactive. This is the point now. Here, this bond is formed between orbitals. Those are 5sp3, and for bromine, this is 3sp3. Iodine belongs to the fifth period and bromine belongs to third period. Here, the difference in principal quantum number is 2. The more the difference in principal quantum number, the bond will be weaker. Here we see the bond between two iodine atoms is formed by the overlap of 5sp3 orbital and 5sp3 orbital. So here no difference between principal quantum numbers. So this bond, that is the bond between two iodine atoms, will be stronger than this bond between iodine and bromine. Similarly, here we see that this bond is formed between two orbitals. Those are 3sp3 hybrid orbital and 3sp3 hybrid orbital. So here as well, no difference in principal quantum number. That is why interhalogen compounds are more reactive than individual halogens. The compound that breaks easily, that will be more reactive. That is, the compounds that poses bonds, weaker bonds, that will be more reactive. Here, iodine monobromide poses weaker bond. That is why this interhalogen compound will be more reactive than individual halogens. This is all about interhalogen compounds. No more today. Thank you very much.